Current AI coding assistants generate massive blocks of text, but still require a human to compile, test, and execute the code. Google Antigravity addresses this bottleneck through an agent-first architecture. In an agent-first architecture, the AI acts as an autonomous actor capable of planning and executing complex tasks, moving away from passive systems that only respond to individual prompts. This changes the researcher's role. You move from writing syntax to managing autonomous systems. With Antigravity, academic faculty can build custom research tools like data dashboards or data pipelines by delegating the software build process directly to the Gemini 3 Pro model. By removing the need to memorize syntax, researchers can focus entirely on experimental design and logic. This side-by-side comparison shows the difference. On the right, a fully functional finance risk dashboard runs live inside the Antigravity multi-panel interface. This tool was generated from a single, high-level natural language command entered into the Agent Manager panel. This workflow follows 3 phases. First, describe, where the researcher inputs the project intent and constraints. Next, plan and create. The AI writes an implementation plan mapping out the architecture. Finally, verify, where the AI autonomously tests its output against that plan. This workflow changes the IDE from a text editor into a mission control center, mirroring the process of delegating a project to a human research assistant. IDE, or Integrated Development Environment, is a software application that provides comprehensive facilities to computer programmers for software development. The mechanism that allows the agent to execute its plan is called multi-surface execution. The first surface is the text editor. Here, the agent autonomously writes, refactors, and manages multiple files simultaneously. The second surface is the terminal. The agent independently runs commands to install necessary dependencies, such as using package managers to load external libraries. The third surface is the integrated browser. The agent navigates web applications directly to visually test UI changes and logic. UI, or user interface, is the graphical layout of an application that a user interacts with. The agent synchronizes these 3 surfaces to test and debug its own work, bypassing the need to pause for human input. The researcher observes this simultaneous execution across all panels in real time, easily maintaining complete transparency into the automated build process. Multi-surface execution automates the manual cycle of software development, reducing the time required for technical setup. This chasm represents the trust gap, the risk associated with delegating complex logic to a black box AI. Researchers often lack the time to manually review every line of generated syntax for errors or AI hallucinations. Antigravity addresses this through a system called artifacts. The agent generates planning artifacts, markdown task lists, architecture diagrams, and detailed implementation logic documents. It also produces execution artifacts, saved terminal logs, screenshots, and recorded browser walkthroughs of the finished tool. These deliverables establish a transparent audit trail of the agent's logic and decision-making process. Researchers can intervene by leaving comments directly on these artifacts, similar to editing a shared document, to course-correct the agent's behavior. The artifact system shifts the academic's focus from debugging raw syntax to verifying system behavior. Overloading an AI's memory with too many global lab rules or formatting standards creates a technical bottleneck. LLM, or large language model, is a type of AI trained on vast amounts of text to understand and generate language. This overload causes context saturation, which leads to hallucinations and the AI ignoring specific instructions. To prevent this, Antigravity uses agent skills. These are directory packages containing a skill.md file that isolate distinct standards and protocols. A researcher can define a standard operating procedure, such as data migration rules, once inside a single skill package. The framework behind this is called progressive disclosure. Under progressive disclosure, skills remain dormant in the background to preserve the AI's active memory. The agent retrieves and injects a specific skill into its active context only when the user's prompt requires that expertise. This targeted injection avoids the memory constraints inherent in long, static system prompts. Progressive disclosure ensures the AI acts as a focused specialist for every unique task, reliably adhering to institutional standards without cognitive overload. Antigravity currently operates under specific hardware and economic realities. The platform is in a free public preview, which includes rate limits on the Gemini 3 Pro models. Users can monitor the AGQ tracker extension to manage these limits. AGQ stands for Anti-Gravity Quota, a metric that tracks a user's remaining computational allowance for specific AI models. For security, researchers should use agent-assisted mode. This forces the AI to request human approval before executing terminal commands or altering local files. Managing these hardware and economic constraints is a necessary step in maintaining a secure research workflow. Computer science is evolving toward intent engineering, a practice where the developer defines the desired outcome and allows the system to manage the underlying implementation. A researcher can manage an entire swarm of specialist AI agents, increasing their operational capacity. This accessibility allows faculty in non-computer science disciplines to prototype digital tools independently. By lowering the technical barrier to creating custom software, researchers can prototype and iterate on experimental environments without the traditional overhead of a dedicated engineering team. Google Antigravity functions as an autonomous partner, providing an auditable pipeline that translates scientific objectives into verified executable code.